开启录制，然后好，跟着我的。怎么那么累个啊？
你的手机有在身上？
有啊。
你有没有？
我没有用那个2段式认证。
对，然后你顺便去那下载一下那个东西。
哪一个 ？OK。老师放哪边啊？
在那个教材里面。
哦，在教材里面。是哪个教材？哪一个 ？OS Part 2的。
Part 3吧。
Part 3的。
应该是吧。没真
然
配置，
后
不是你看一下公告。New message page in Part 2 Part
，Message Pacing PPT。
那
是之前的，是不是？
对 ，Part 2的 Part 2。
Message Pacing。
对，拿下来。先开个公密器，看一下好了。
DS。OK。Google Meet 是在 Announcement。
最下面。上面一个。
等我看看 New Version Class Schedule。
还要登录机球。
所以老师上次，是上到 Message Pacing 那边吗？
我不知道他上哪里啊。允许。再来一次。
行。跑掉是不是？
应该是。你回到那 Google Meet 那边，按上页。
我直接按上页就可以了。为什么是这个模式？这什么意思？
先加入。
好大哦！为什么这台这么大？
你用一台2013年的电脑。
不是，这2017耶。
2017。
比我跟我用那个2014还比较没大。
先滚。允许。确实很累。刚刚老师跟我说他不要上课，今天下雨不想来学校。 直接发火，老师你不能这样。
好，不知道是哪一个。
会关掉吗？
Dispute file system。
对啊，就是。所以我刚教到这里，好的，没事没事去陪审。
这结束了，这最底下。
我记得没事去陪审，好像才刚教的。没有刚教，记得。那像是什么？我现在没事去陪审那边。
这是我刚下载的新的版本。
哦，欢迎回来。我记得上早我看到那个。
啊，我有看到这边，我有看到这边。
是啊。
对。
Rocking Stand。就上早我看到。
好像在这附近。应该在这附近。
我那 PPT 已经做好了，然后我等下把 PPT 先把会有 PDF 让它弄。
老师，你上次上到这边吗？还是哪边？这附近。
往下，再往下。
再往下。
再往哪里去？
这边。老师，我帮你用一下。对，好。
在这里。
OK， 好。
还是我等一下给老师看完之后，今天晚上先不要报，然后明天早上是不是要去看马来西亚那个？对。然后那我明天下午的时候也顺便跟老师讨论，就我等下给老师看完之后，我就直接开始做修改，然后晚上的话我就先 pass， 然后我明天的时候我就再跟老师。
对啊，不是我说那个电视机还没接好啊。
你老是说电视机那个？
对啊。
因为那个就是还要一条 HDMI 线。
对啊，你们那线没有人去弄来。
我到时候去申一下。
啊。因为我看那个业务会好像还有一些嘛。
不是，那5200块那个不是要买设备吗？就是1万块以上。
那跟系上换就好了。跟系上换业务会你问一下。
Okay. Last week we stopped here. Okay. We discussed the group communication and the major reason to require group communication. Sometimes we need replicated databases or in client server applications. If there are multiple servers, they can provide similar functionality. Then the client may be able to send a request to those servers and get any of the response. Okay. So and so on. Okay. So here is a basic example of the high available web servers. Most popular internet services, they have these dedicated web servers. Okay, and so for any web client, when you connect to a particular server, for example, the Google or Facebook, you are not connect to their main server or main servers. You connect to a local front end. Okay, and then those front end and in general there are multiple front ends for this kind of services. Okay, and which front end your request will be sent to depends on the routing strategy. Okay, and so most of the time for this popular or highly demanded internet services, they have a lot of front-end server in different data centers, for example. Okay, say if you connect to internet through the service provided by, say, HiNet, and then maybe they may have a front end in HiNet data centers, and for some users they may connect to internet. Go through the other telecom company, for example, the Taiwan Data or Far East Telecom and so on. And they all have their own switching centers. So for these popular internet services, they have a lot of front-end server in those different vendors or different internet provider, service providers, switching centers. Okay, and depends on where you connect to the internet. Your request will be directed to different front-end server, and this front-end they are replicated web servers. Okay, because they all provide the same functionality. Okay, for the clients. Okay. And here, in general, a group may be defined as a closed group or open group. Okay, the difference is like this. Okay? A closed group means that only those members in this group can send a message to the group members, to all the group members. Okay, so a process, of course, the outside process they cannot send message to the whole group, but they can send individual message to individual members. Okay? And an open group usually means that any process, either in a group or outside the group, they can send message to the whole group. Okay? So the major difference is something like that. For closed group, only those members, the group members, they can send message to the whole group. But for open group, any process can send a message to the whole group. Okay. To the whole group means all the group members will receive the same messages. Okay. So for this kind of group communication requirement or mechanism, usually we need to have a mechanism to manage the group members. Okay. And usually we need to have a way to create, delete, or allow process join or leave a particular group in any given times. So most common available way is to use a centralized group server to manage the group of members and their membership information. Okay? So this central group server, they will maintain a list of members. Okay, for each group. Okay, so for each group, you have a set of a list of process IDs. So all the requests to create group, delete or add members, remove members, they are managed by these central group servers. The advantage for this kind of mechanism is that it's simple, easy to implement, and manage and maintain. Of course, as usual, the disadvantage is that there's a single point of failure and performance bottleneck. Okay. So in general, to send a message to a group, we need to maintain not only the group members, and each group will have a group addressing problem. Okay. It's like naming for a process. Okay, so we need to have a addressing mechanism for a group. Okay, in general, most systems use this two-level naming scheme. Okay, for group addressing problem. The high-level group name usually is human-readable ASCII strings. Okay, and the name usually is independent of the location information of any of the group process in the groups. And the low-level group name depends on what kind of network the system, the underlying system provide. For example, if the underlying network system they provide multicasting facility, so the network is we call it multicast enabled network. Okay. Then this usually the multicast address. Okay. In this kind of network, every multicast would have a multicast address to specify a set of processes. Okay. And so this can be used as a low-level name. So a packet sent to a multicast address automatically delivered to all the machine listening in the address. Here, this multicast enabled address, usually this multicast address represents a set of IP address. Okay. So each multicast address mapped to a set of IP address. Okay. So it's in the host level. Okay. So the message will deliver to those hosts. Okay. They are associated with a particular multicast address. So if the underlying system supports this, then this group server will maintain associate each group. For each group, they will create a map of multicast address for the particular groups. Okay, so because the group member is in process level, it's not a host level, so it's possible multiple process in the same host may belong to the same group. Okay. So mapping actually is a two-layer mapping. Okay? You first map to those hosts. They contain some process in a particular group. And when the message came to arrive to that particular host, the host will check the group member information and then deliver this message to those process that belong to the same particular group. Okay. And if the underlying network support broadcast system, then the broadcast address can be used as a low-level name. So packet send to a particular group automatically map to a broadcast message for all the hosts. Again, okay, because now every host will receive every broadcast messages. Okay, then so every host they need to check this particular broadcast message is for any of the process in its host. Okay. So if not, then the package just simply be discarded. Okay. If some of the process in the host is belong to this particular group, then the host will deliver the message to those processes. Okay. So either way, if a network support multicast or support broadcast, then this physical underlying multicast address or broadcast can be used as the low-level message. Of course, it requires the host level system library. They need to do the second layer of the mappings. They need to find out there any process in the host that belong to a particular group or not. Okay? Because for broadcasting, especially for broadcast, all groups will have the same low-level names, the broadcast address. So any message will be received by all the hosts. So every host must check, okay, this message is belong to for a particular group, and then you need to find out any process is in the host is belong to that group or not. Okay. The last possible is if the underlying system network did not support multicast or broadcast, then the the central group server will maintain a list of hosts. Okay, and those hosts have a process in a group. They need to maintain this information. So this list will be maintained in the central group server. Okay, and so when the sender tries to send to a particular group, they first check with the central group server to find out to retrieve this list, and then send message, use point-to-point message to send message to each host. Again, the host level network system will then deliver this message to a particular process belong to the group. Okay, so that's the way to handle these group communications. So here we'll discuss, give a more detail to how the message is delivered in the multicasting in the group. Okay, so a sender send a message to a group. They will specify its group high-level name, right? So, and the kernel of the sending process host, okay, the sending host, first they will contact the central group server to obtain the low-level name of the group. Okay. And this low-level name either is a distal process ID with a multi-case address or with a broadcast address, okay, and so on, okay, or a distal host, okay, with a distal host, okay, depends on what kind of low-level naming mechanism. Then this distal PID will be embedded into the message as a message header. Okay. And then they use the low-level address to send out this message. Okay, either as a multi-case message, or as a broadcast message, or as a set of point-to-point message to those hosts. And the kernel, okay. And so when the message reaches the host, okay, the kernel of that host, they first extract this PID list and then forward the message to those processes in the host. Okay, so the list of PID not only contain the PID, they will contain the host as well. So the host will know which process is in the host and so on. So that's the detail of this handle message delivery. In handling or manage these multi-case messages or group communication messages, okay, it depends on the message. It can be buffered or without buffered. Okay, the semantic will be a little bit different, okay? Because the delivery of this multi-case usually is an asynchronous communication mechanism. The reason for this is that if not all the members of a particular group are ready to receive, then the message need to be queued in some way, buffered in some way. Okay, but so the semantic depends on how you implement this. If the implementation is buffered or unbuffered, the semantic will be different. For unbuffered multi-case, then the system will guarantee they can only deliver this message to those processes in this particular group. They are ready to receive. Okay, for those process, although they are in the group but they are not ready to receive, then they will not be able to deliver because the underlying the system did not provide buffer. Okay, so if the system provide buffer, then it's possible we can guarantee to deliver this message to all the processes in the group. Okay, so the semantic will be different. It depends on message can be buffered or without buffer. Okay. So when you use this a group communication facility by a network system. You need to know these messages are buffered or not buffered. You need to first figure out what kind of semantic the system provide. Okay, they either provide this buffered multicast or unbuffered multicast. Then the semantic will be different. Okay. So the implementation of this multicasting in general, they have these two kinds of semantics. One is central semantics. Okay? For example, if the system provides buffers, okay, if the system did not provide buffer, then it's impossible to implement central. Okay, so for system provide buffers, then there's two kinds of implementations. Okay, or you can say two kinds of semantics. Okay, because the implementation are different, and so the semantic is also different. Also, okay. For this central semantic, usually message will be copied to each process, okay, in a group, okay, and because of that is buffered, so every process eventually will receive the particular message. Okay. Now the second implementation is we call bulletin board type of semantics. That means the message instead of delivered by the multicasting, okay, they use a channel or bulletin board or a queue, okay, or a repository for each multicast message. Okay. So a message to a multicast is addressed to a particular channel. That means a group in this implementation, a communication group will be associated with a particular repository, we call it channel, or a board. Okay, so each board corresponding to a group or process. So whenever you try to send a message to a particular group, the system will put this message into the repository for that particular channel. Then individual process in the group, they can just retrieve the information, retrieve the message from the board or from the channel, from the repository. Okay, and for this kind of implementation, the message will never be dropped or deleted. They need to be removed explicitly by the sender. Okay, so whenever you put something in there, only the sender is allowed to remove it later. So when the sender find out all the corresponding receiver has access that particular message, then it can remove. Otherwise, because it's a repository, so the message information is always kept there. Okay, so this kind of implementation or semantic is different, but they also achieve the multicasting purpose. Okay, so receiving process, they just copy from this board. So instead of they remove the message from the buffer, okay, the message will never be removed, okay, unless deleted by the sender itself explicitly. Okay. So the group become, if the system provides this kind of implementation, then usually this group, the multi-group, is some kind, usually is an implicit group. Whenever a process join to a board, okay, when we allow to join, then it become a group member of that particular group. Okay, so whenever you decide that you want to read, you just read. Okay. Another property in multicasting is the reliability, because here, when the purpose of we send a message to multiple receiver usually means one specific purpose is that this server they may handle, they may provide the same functionality. Okay, so you send a message out, but you only expect one message reply from some server. maybe enough. Okay, so depends on how many response the sender expect. We call it reliability of this. They use this term. Okay, the reliability in here means how many response that the sender expect to receive. Okay, in this, the degree of reliability is expressed as a response message expected. So it's possible you did not expect any response, then this we call it zero reliability. Okay, if no response is expected, that means the sender usually is just the message generator. It generates message and send out. It did not expect the receiver response. Okay, and typical is event signal, event generator. Okay, or time signal generator. This kind of sender, they just generate this event or generate this signal, okay, to those desired or interested receivers. You do not expect any response. Okay. The second one is one reliability. That means one reliable. That means you only expect one message return. It's enough for the sender to continue its operation. Okay. The third one is M out of N reliable. That means when you send out a message to N receiver, it expects M response. Here the M usually is less than N. Okay. One typical example is for the photo erasing codes in rates or whatever. Okay, this kind of similar. So the N receivers and sender expect M response from the receiver. The erasing code or rate, they have this kind of property. Okay, where the message, the original data was coded to become N partitions. Okay, and any of M partition, if you accumulate M partition out of this N partition, then it's possible to regenerate the original data. So that's this erasure coding mechanism. Okay, erasure coding is a set of mathematical functions. Okay, they can provide this facility. Originally you have a message, the data size, some size, and then you partition using this mechanism. You generate a small set or partial partition of this original data. Okay, and any out of these N partitions, if you can be used to reproduce the original data. So, so the purpose for this is that means if these N small partitions, as long as M of them are available, then it's possible you always can recreate the original data. Okay, so by using this to achieve the high availability, okay, you don't need. So in general, this M usually is far less than N. Okay, and last one is all reliable. That means sender expect a response from all the receivers. Okay. So this reliability means the expected response is either 0, 1, or M or N or O. Okay. The atomic multi-case is a special term for the multi-case information. Okay. That means that the multi-case message either received by all the members or none of them. Okay, no one received this message. So this kind of property, or we call it atomic multicasting. Okay, so if a multicasting system provide this semantics, that means it guarantees either deliver message to all of the member, or you hold the message not delivered to all. If some of the process is not ready, then it will not deliver. Okay. So that's the term means atomic here. Okay. So in general, this atomic market only makes sense for these all reliable applications. That means if your message is intended to all the receiver and you expect all of them give a response. Otherwise, there's no point to use this atomic multicast. Okay, because either if you are not expect response from all the members, then you don't care. They all of them receive or none of them receive. Okay. So this atomic multicasting usually only makes sense if the application require all the receiver receive the message and also generate a response. Then this atomic property become meaningful for this kind of application. Okay. So it's a property, a special property, but not all application require this one, because only this kind of application, okay, they may require this atomic property. Okay. A simple mechanism to implement this atomic is you just use timeout acknowledgement with retransmission, okay, for the message. As long as no process fail during this message delivery time intervals. Okay, if some of them fail, then because this all reliable property requirement, then this message need to be undelivered in some sense. Okay, they need to wait until all the process become ready. It's not crushed. So all the process in the group, they cannot crush during this message delivery. Otherwise, the message will be taken off. Okay, as nobody received. Okay. They need to be undo for the message delivery. Okay. So to preserve this property, the multicasting facility, they need to have a way to undo any message delivery, a partial message delivery, or whatever. Okay? Because if some of the process crash during this message delivery, then all the process they need to be undo the receiving activities. Okay? So here here we atomic multicasting, we call it photon atomic multicasting. The semantic is a little bit different to this all reliable atomic multicasting. Okay, here means if the system allow some process crash, okay, some member of the process crash during this message delivery, but as long as all the available process they will receive the same message. Okay, so they release the constraint of atomic to a little bit, and not for all the process in the group, but only for those processes they are currently operational. Okay, for those failed process, you don't care, as long as those operational process they all receive or none of them receive. Okay, so this is the semantic or the meaning of this photon atomic means. Okay, so it's a simple photon atomic. Then the algorithm will be something like that. So first sender will send a message to all the members of the group and set a timer, and this can be used. Okay. Well, when the process receives a message, a particular message sent out, okay, if by this simple photon atomic method, every message sent out by the sender will carry a sequence number, okay, and with sender's ID, something like that. Okay, so whenever you receive a message, and you will check, you will log this message is a duplicate or not. is if it's the first time you receive this particular message, then you send the message, you forward the message to all the members in the group, okay, also. And then you set a timer, okay. And if it's a duplicate you receive, then you just discard, okay. So by using this flooding mechanism, okay, whenever you receive the new message, then you just forward to all the members, you know, okay, all the members, they are still available, they are still operational, okay. Then eventually all the members in the group, they will either receive the message or they crash during this process, okay. So but eventually all the survival process, they will get the message, okay. So that's the simple way to handle this atomic multicast. If we only care about the survival process, they all receive, okay, not all of them, okay, because some process fail, you are not willing to wait for their recovery, okay. You just forget about them, okay. So as long as survival process, they all receive the same message, then it's alright, okay. So the semantic is a little bit different to the real, this we call it all reliable atomic multicast, okay. This is a fault-tolerant atomic multicast. The meaning is different, okay. So for this one-to-many or sometimes we call it multicast primitive facilities, most systems they use this same group system called or API to distinguish the one-to-one message send, okay. The reason for this then it's much easier to implement. If we use the send for both purposes, then the parameter will become very tedious. You need to a lot of parameter to specify the meaning of this send. So most systems they use a simple way. You just create a new API for this group application. Okay. So the implementation for send, you use a name server to find out the receiver. Okay. Again, usually you have a two-level processing, okay. And for this group application, you consult with the central group server to find out, okay, either to find out the low-level group IDs, okay. So and for this API, usually we may have two optional parameters. One is for specify the degree of reliability. Okay, you can specify 0, 1, N, or O. Okay, depends on what kind of application, the requirement of the applications. And the second extra parameter is the atomicity. Okay, if it's all reliable, then you need to specify. You require atomic or photon-atomic. Okay, they are different. Okay. So you have a second optional parameter to specify that. Okay. So that's most multicasting system, the way they use for these APIs. Okay. Now here we'll discuss the second type of group communication. We call many-to-one communication. Okay. That usually means multiple sender send out message to a single receiver, okay? And a single receiver, this particular single receiver, then it may be selective or non-selective. Selective means the receiver can specify a particular senders, okay? So only the message generated from this particular server arrive, then the message will be delivered. Okay? So, but this selective operation is similar to receive, to normal receive, right? But with a specified sender address, okay? It's similar to that. Okay? So in general, this is not a case we used for this M2 one. The second one is non-selective receive. Usually, you just specify. You expect a message, okay, and the message can from the set of senders, okay. But so it's different to this non-specified receiver in the receive. In the asymmetric matrix direct communication, we remember in direct communication we said the receive you may use symmetric method in the receive specify the sender's address, or you use asymmetric method. The receiver did not specify the address of the receiver. Instead, you use the output argument to capture the real receiver's ID or whatever, right? But here, this is similar to the asymmetric, but not, because it's not any receiver, any sender. You specify a set of senders, okay, but instead of one particular sender, okay? So any sender from this set is desirable, okay? So that's this non-selective receive input. Okay. So any sender in this set, when they send a message to the receiver, then this message will be exchanged, delivered to the receiver. Okay. So this non-selective will generate non-deterministic, because we don't know which message actually delivered. If there are multiple senders, they send out a message to the, and this sender are all in this set. Okay, the receiver will only capture one message. Okay, and so which one is non-deterministic? Okay. The last type of group communication is many-to-many communication. That means you have multiple senders send out message to multiple receivers. Okay. And the multi-case, one-to-many, and the many-to-one, they are special case of this many-to-many. Okay. So many-to-many is a more general group communication type. Okay. And because this many-to-many, so we have many senders simultaneously exist, and they all try to send a message to the same group of the members. Okay. So the semantic of this, how to deliver the message to those receivers, become easy. So the order of the delivery become an important issue, because different order delivery to the receivers, they may mean different semantics. Okay. So order the message delivered, they require for some applications. Okay. Otherwise, this receiver, if different receiver, they receive the message by different order, then the outcome of this will be in some cases may become inconsistent to the application requirements. Okay. For example, if these receivers are replicated servers, replicated databases, then this update, this multi-case message, they are update requests. Okay. Then for those replicated database servers, the delivery should be in the same order. Okay. Otherwise, the update, the outcome of this replicated server may become different, may become inconsistent. Okay, if they handle this update in different sequence. Okay, so that's the meaning here. So the delivery of this message may become important for these many-to-many applications. Okay. So order the message delivery usually we require message sequence. Okay, So in some sense, that a center they initiate a multicast only the previous multicast message has been received in some sense, or when two multicast came from the same center, right? Then the system must ensure that the first message has been delivered, and then the second message can be delivered. Otherwise, the semantic will be unexpected from the sender's point of view, okay? Because a sender sends out two messages, one after another, right? In general, this means that the first one should be delivered, should be processed by other receiver first, and then the second one, right? So that's the first. So sequencing become important for the, especially for the message generated from the same centers. Okay? And in this many to one, because if the multicasting is in the group computation is in this form, and this is one to many, right? This is many to one. Then the receiver itself become the sequencer because only one receiver, right? So the order always consistent because only one receiver. Okay, so for many to one, you don't worry about the sequencing, but for one to many, the sequence is very important. Okay, so here is an example. If the order are different, for example, we have two centers and they all send message to the same set of receivers. Okay, this is the timeline. Okay, from past to the future. Okay, and if the message delivered to receiver 1 is in M1 and 2, and delivered to receiver 2 is in M2 and M1, then these two receivers they will process these two messages in different orders. Okay, so the result maybe depends on application. Some application they don't care. Okay, some application this ordering is important. So depends on applications. You can specify what kind of ordering delivery of the messaging is your requirement. Okay. So the semantics for this messaging ordering usually have these three ordering semantic. One is absolute ordering. That means all messages are delivered to all receivers in the exact order in which they were sent. So in general, to achieve this, usually we require a synchronized clock in the whole system. Okay, because everybody have the clock, same clock maybe. Then use the clock as a timestamp. So whenever you send out message, you attach a timestamp. So the receiver they will buffer those requests. Okay, and then eventually find out and deliver the process this message according to their timestamp. Okay. So everybody will be the message will be processed in the order of they generate. Okay. So every ordering usually means they require the order is the same as the sending processes order. Okay. Although this sending process you may have multiple senders, but as long as the clock are well synchronized, then it's possible. Okay, but because even those most synchronized system, they usually can only guarantee their synchronization, their clock synchronized within some resolution. For example, they may synchronize within 10 milliseconds, right? So that means every 10 milliseconds they are synchronized. But if the time interval is smaller than 10 milliseconds, then you don't know. Okay? So this absolute ordering usually they can only achieve not in the exactly absolute, but in the clock orders. Okay, in these synchronized clock orders. Okay? And the second one is consistent ordering. Okay, That means because this clock in general is difficult to well synchronized. So as long as these messages are delivered in the same order for all the receiver, and this order may not be necessarily equivalent to the real order, but as long as everybody process this message in the same order, then the application can be satisfied. The requirement of the application can be satisfied. So this we call consistent ordering. Okay. So in general, for most applications, this consistent ordering is enough. Okay, good enough. Okay. The last one is a more released application. Okay, we call causal ordering. So if two same thing events, they have dependence, causal relationship, then their message need to be processed or received according to their causal order. Then this we call causal ordering delivery. Okay. So as long as if two messages they are concurrent, that means they don't have any dependence. Okay. They don't have, then their ordering, their process order become irrelevant. Okay. The receiver can process them in any order. So only those related sending event, their order need to be preserved. Okay. So in general, we have this three kind of ordering. Okay. Let's take a break.
这就是目前的那个。然后你要的话，你可以把它翻这样会比较大。
OK。
然后老师重新看有什么需要加的。因为我觉得这些东西算是已经蛮够紧的了。
所以这个不应该放在前面吗？
老讲放在哪边？
放在 DID 的那里啊。这个应该。
OK， 好，那我都会把它移。
这移到前面，不要放在这应该在最前面就要加。
好，没问题。
因为你刚讲4块嘛，第4块就 SSI， 所以 SSI 的定义讲完以后，就应该讲这一块。
好，没问题。但是我现在有一个问题是，我们的这 scheme 的 control 部分，它是讲的是像是它可以处理任何 ID 里面的资料。它那里面有举个例子是 driver license。它意思说我们 driver license 应该是可以去由我们自己控制，然后就控制好就是删除，然后以及那个去分享。
这个我们不要啊，因为我们目的要为了可以 audit 的，所以它不能随便去改它的东西啊。所以就是为什么我们不是 SSI， 但是我们是很接近 SSI。因为我们的目的就是希望可以被 audit。说 SSI 没办法 audit， 因为你存进去的自己的 information，你随时可以去改，那怎么可以啊？什么日上什么我看改一下，怎么可以？对，所以你是 你是透过 agent verify 过后把它存起来，对不对？那存起来以后，那个东西将来你在 KYC 或怎么样就可以去验证这个事情嘛。你不能自己都不能改，没有人可以改，存那些就存就不能改的。所以我们的 DID 是不能改的，里面的语言是不能改的啊。对，你的血型、你的身份证，对你照片的，或者是你身体资讯，你可能什么指纹啊，什么眼膜啊，对，这是不能改的啊。这个是为什么我们不是真正的 SSI 嘛？但真正其他都达到。你目的就是在，因为真正的 SSI 就没法管，没法包点嘛。对，好。
那就我把这个移上去之后，然后其他还有需要做修正吗？
其他就差不多，就这样啊。
那我到时候再写一份组织稿给老师。
对啊。
然后，因为他在这边的话都是已经开发的 ID 啦，他这边都是那个网络上。对，网络上有开发的 ID。
那你有没有那个？
我有一篇论文是专门。
不是，我知道，你就把这几篇这几个东西cite 就是有个 reference 啦，就是你在讲完以后，这些 paper 的，就是列出来然后我们在讲我们 application 的时候，我们在讲完我们的这个讲完这个嘛，然后我讲完我们的 application 的时候，然后再把我们目前的一些成果把它列出来，这样。
我是说那个像是他 gas consumption 那些。
不是，就是说我们目前的成果，就是说在这 application 这一块，我们做了哪几个了？我们再讲一个，对，都会写出，因为有些有 publish 嘛，有些 conference 啊，有什么都把它列出来。
OK。
啊，就是最近的节目把它列出来，这样。
好。
好，就这样。哎，那个，你叫那个伟成想一想，就 DID 的部分呢 ，DID 我们现在是你要回去确认嘛，对不对？啊，那能不能他送出来就用 zero knowledge 的 proof 的方式，就让他不需要回去确认，只是说你给出来的那个 private key 或者是那个 address 就包含了一个就让人家可以直接拿到那个东西去验证。
就是用这个。
对，用 GKP 当做你的 address 或者 GKP， 就 address 里面就含了 GKP， 对，所以我拿到那个东西，我直接就可以 verify， 不需要回去
回去再做验证。
对，就是他那边就叫他 focus 在这一块就好，其他的那就不要，就是因为这一块可以弄的话，其他就可以弄，对，就是说但是这个可以弄的好处是在你离线都可以做嘛。你不需要每次都回到那里去嘛？
对。
好，
那像是那个，那我想说 ，DID 券，然后老师想说 DID exchange 券，对不对？
对啊。
那我们 DID exchange 券，要不然就是给下面的人去做。
对啊。
给那个，因为我是已经想说给帮你去做。
可以啊，没有问题啊。
那应该，所以就是等下去跟伟成讲说，看他要不要把这个应用在那个。
只要应用在 DID 的那个 verification 就好了。因为这一块能够先做好，就很重要啦。
OK。
对，就是我们本身现在是弄一个 address， 对，那你这个 address 如果能够不需要回去 check， 而是直接
可以生出验证的程度。
对。然后你看他说，就目的就是说，让你拿到这个东西，就是说我要做 KYC 的时候，就我今天要拿这个，我要到 application 券，我要申请账号，对 ，application 券的管理者。你给我这个东西，我就可以直接验证，然后就知道你就是那个人，对，你就是你说的那个人那你的 DID 就是这一个有被注册过在那里的你需要达到是这个目的嘛，而且你就是你讲的那个人，对，等等那样的话才会比较 make sense 啦就是你省掉一个回去 check 的，对，那另外一个就是说我们现在的做法是你去上面抓东西下来。那另外一种考虑就是说，我要回去测的时候，我不需要抓东西，我是把 local generate 东西送上去，在那边去做比较。也就是说，我看我 KYC 要做什么，对，例如说我 KYC 我看你的我身份证字号跟你的照片，对，我把你照起来，然后你身份证字号包起来，送回去，你给我哪一个 address， 对，我送回去，那边那个什么 country 他就拿这两个东西跟他存的资料来比，对。比对的，他就return告诉你说，对， 对，这样也可以。这样的话好处是什么？我不需要把东西抓下来啊，你抓下来就容易曝光啊。我是丢上去的，确认啊。这也是另外一种啊。就有些KYC 可能做到这样就可以了，我不需要因为我例如说我在银行开户对，或怎么样，我这边通常有个照相机嘛，照相然后你就输入你的身份证字号对，啊或者你把你的那个身份证秀出来，他就把你身份证资料跟照片丢上去，我就不用存嘛，我就丢上去，那回来成功，啊确认，这样也可以啊，这也是另外一种了啊。那样好处就是说我丢上去的时候，我其实会把它加密嘛，但是我用的是说变成是这个 agent 的 public key 去加密，或者是 agent 的 private key 去加密，对，那送上去上面那边它就可以，它就打开，那知道你这个 agent 的 public key 或怎么样啊，那它就可以跟里面的东西来比嘛。好。Okay, we are back. So for this absolute ordering, usually we require a synchronized clock and use this timestamp as the sequence number. So receiving host, they deliver this message according to this timestamp. Okay, this is a example. For example, the T1 is less than T2, then the message M1 need to be delivered before and two. Okay. And the consistent ordering means the sender, for example, okay, the sending host, one way is that they send a confirmation to a spatial process. For example, this is one implementation. So a system may use a centralized sequential. Okay. So a particular process is dedicated to doing this sequential. Okay. Remember here we say for this many to one, the receiver itself becomes the sequential, right? So using this concept, so we just designate one particular process as this sequential. So before you send real message to the whole group, you send a request control message to this sequential process. Then they will return a sequence number, and then you attach this kernel to your multi-case message. Okay. So then the receiver for this multi-case they will deliver according to this sequence number. Then so this consistent ordering can be guaranteed. Okay. Of course, this is a simple implementation. Okay. Because you have a single sequential. If as long as this group communication, the activity of the group communication, the frequency is not too high, okay, then it's good enough. Okay. Otherwise, if the load for this group communication is very high, then of course the sequential becomes the central point of failure and bottleneck. Okay, because everybody need to consult first. Okay. So, but if it's not the case, okay, the activity for this group communication is not too high, then that's a good implementation. It's good enough. Okay. So this we call it consistent ordering. Okay. So everybody have the same order to process those messages. Okay. And here is an implementation. They implement this consistent ordering without using a single sequential. Okay. Because this protocol was proposed in this ISIS
distributed database systems. Okay, they can provide consistent ordering. Okay? The ordering is something like this. Okay, when the sender they try to send a message, multi-case message, they first assign a temporary sequence number. Okay, so every sender uses its own way to generate a temporary sequence number. Okay, and then send this control message is a control message to all the members of the group. So before sending real data, they send out this control message with this temporary sequence number. And of course, this temporary sequence must satisfy some constraint. Is that it must greater than any previous used sequence number by these senders. Okay, so you cannot generate a sequence number smaller than anything. And here we mean used, not generated by the sender. That means any sequence number has been found or received by this particular sender, either generated by itself or received from others. Okay, you need to generate a sequence number temporary greater than everything so far. Okay, you know. Okay, and then you send out to every members. So when receiving this temporary sequence number, the confirmation with this temporary sequence number, okay, every receiver return a proposed sequence number, okay, and the proposed sequence number for a particular member I, for example, they use this formula, okay. So F and P, the maximum of F plus 1 plus I over N. I is the identifier of this member. Okay. For example, every member, you have an N member, then every member will have a member ID from 1 to N. Okay. So this one is a tiebreaker. Okay. The first, these two parts, the output of these two parts may be the same. Okay. For two messages generated by two different senders. But this one, okay, this one will tiebreak, become a tiebreaker. Okay. So F max is the largest final sequence number. Okay, agreed by the group. Okay, and the P max is the largest proposed sequence number. Okay, previous proposed sequence number by this particular member I. Okay, and either one, which one is bigger than is one plus 1 because you try to generate a new proposed sequence number and then plus this sequence number. Okay. So every member will use this way to generate a proposed sequence number and send back to the original sender. Okay. When receive all the proposed sequence number from all the receivers, the sender will select the largest one, okay, as the final sequence number for the message and send it out to the owner member. And this message, we call it commit message, okay, and this final sequence number will be embedded. Okay. Because the selection of this final sequence is guaranteed to be unique, okay, because the message generated from the same receiver, receiver, because every time you propose number, you always get a greater one, right? Plus 1, at least 1. So when you propose a sequence number, the next time you propose will always greater than the previous one. Okay, so and this tiebreaker can be used to distinguish. The advantage for this is that the final sequence is always unique. Okay, but it becomes a real number here. This will a fraction of a number, right? So the value will become real number. Okay. The problem for real number is that it's difficult to make sure the smallest value so far for a receiver, the final sequence number received for a particular receiver, you don't know that's the real smallest one or not. Maybe some message is still exchanging. Okay, so the problem for this is that okay. Unless you need to recall, okay, some previous delivered information in some sense. For example, you do some if the every sender, if the receiver has received all the messages generated from other senders, okay, you log the last message, last final sequence number generated from every sender. So then it becomes possible when you to find out the current smallest final sequence number is really the smallest one. Okay. So the problem is here is this. Okay. Although you get a unique final sequence number, but you don't know how long you need to wait to make sure the smallest one is really the smallest one. Okay, it's that any pending message wrong. Okay, and so on. So that's the mechanism used in ISIS, okay, in this particular distributed system. And these are related references. And for cordial ordering, okay, that means we don't require all the receiver process all message in the same order, but only those message they have cordial dependence. Then you need to make sure their processing order are consistent with this cordial order. Okay, so this is a more weaker ordering semantics. Okay, for some applications that's enough. Okay. Actually, many applications this usually is good enough. Okay. For example, here we have an example. We have S1 and S2, and S1 general M1, and M for these three, and S2 general M2, and also this R1 not only is a receiver, it also generates a message we call it M3. Okay, so from this timeline, we know that the M3 which depends on M1 because R1 after receive M1, then it may generate M3. Okay. And so M1 and M3 has this causal relationship. But M1 and M2, because they are generated by two different senders, and these two messages before these two senders, they don't have previous relationships, so these two is concurrent. They are concurrent. Okay, and M2 and M3, again, this M3 depends on M1, but it's not related to M2. So M2 and M3 is also concurrent. So therefore, the delivery, the only concern is M1 must be processed before M3. Okay. So here for R1, M1 is processed before M3 because M3 up generally. For R2, M1 is received before M3, so it's good. For R3, M1 is received before M3, it's also good. But the M2 can be in any order compared with this M1 or M2, okay, or M3. Okay. And so this is a causal ordering semantic. Okay. They meet the requirement of causal ordering consistency. Okay? And here is an example to handle this cordial ordering, to provide this cordial order, ensure this cordial order. Okay? We call it cordial ordering broadcasting protocol. Okay? In this algorithm, every member of this group they maintain a vector, okay, not of n elements. Okay? Because assume the system has n members, okay, and this n element corresponds to one of the process. And the ith element we call the largest sequence number received by this particular member from member I. Okay, so any member, its ith item in this vector, we call the largest sequence number generated, sent out from member I, okay, and received by this particular member. So before sending a message, the process they increment its sequence number of its own element, okay, in this vector, okay, in this maintained vector. You don't change others because others are the sequence number generated from other members. Okay, only its own member number can be modified by itself. Okay, and then send out a message with this vector as a timestamp. Okay, so sometimes this protocol we call it vector timestamp. Right? It's a vector, not a single value of the timestamp. So when we receive a message with this vector timestamp, okay, the receiving host, the first buffer the message. Okay, it did not deliver yet. Okay, just buffer in there, and let S be the vector attached in this received message. Okay, and R is the vector maintained by the receiver itself. Okay, receiver maintain a vector. Every message attach a vector as a timestamp. Okay, so this is attached in the message. This is maintained by the receiver. Okay, then I with the unique ID of the sender. So if the message is sent from the sender I, okay. If SI, the message in attached vector SI is equal to Ri plus 1. That means from the point of view of this receiver, this ith member, previous ith member message are all received. Okay, this one is the newest one, and all the other messages generated by this member I are all received by this particular receiver. Okay, this condition means that, okay, if S1 Si equal to Ri plus 1 means that, and also for all the other J not equal to I also, that means all the other members their receive J means their message and this Sj is less than or equal to Rj. That means sender did not, this new message, this particular message generated by this sender I, okay, it did not depend on any message which is not received by the current receiver yet. Okay, so this Sj less than or equal to Rj means that this newly accepted or received message sent from I did not depend on any other message, so not received by the current receiver yet. Otherwise, this will not true. Okay, so this message can be delivered because it did not depend on anything. It's unknown to the receiver yet. Okay, so all the cordial dependencies are fulfilled. So this message can be delivered, okay, to the application. Otherwise, That means some of them is not satisfied for some message generated from some particular members. So this message is left in the buffer. Okay. But either way, either this true or not, then this RI always updated become SI, because now the new message is secret number will be SI. So you update this recorded vector. Okay. So every receiver would have a set of message in its buffers. Okay. Periodically, this undelivered message will be checked to see, because this condition, whenever you receive a message, you may update some of this, right? So this update may make some of this condition become true. So some undelivered message may become now deliverable. Okay, so that's this event does. So periodically, you check every undelivered message to test whether now it's become deliverable or not. Okay? So, for example, that the undelivered message is sent from member I. Okay? If SI equal to RI, okay, because it always is the last one, and for all the other, this SJ are less than or equal to RGA. That means they all become, this R is already been updated. So this condition now become true. Then this message becomes deliverable. Then you can deliver. Okay. So that's the text of this is just ensure. Okay. It's not miss anything. Okay. And two messages from the same center are always causally related. And this test is just make sure not from others they are all causally independent, okay, in some sense. So dependency is always fulfilled. Okay? But here is an example. Okay? If we have a system with 4 members, okay, and this is A, B, C, D, A is in the first index, and the current vector maintained by these 4 processes are something like this. Okay? Their vector value may be different. Okay? So if process A send out a new message, then the vector of this entry, this element will become 4251 as a new vector. Okay? And this will attach to the message. And this message is sent to 3 members. For process B, this SI equal to RI plus 1, and all the other S are less than or equal to R. Okay, so this message can be delivered for process B. Now we compare this one with this one. Okay, SI is not equal to RI plus 1. Actually, it's RI plus 2. That means there's a message is missing for this. See, send a message sent out from process A is not received by this process yet. But for some reason, this later message was accepted or received by the host before the previous one. Okay. So every message may be delivered, goes through different routes or whatever reasons. Okay. But anyway, this message cannot be delivered from the point of view of process C, so it needs to be queued in this buffer. And for process D, okay, this SI is equal to RI plus 1. However, okay, this one, S3 is not less than or equal to R3. So that means some message is not received by this one, was used to generate this message, right? So this message cannot be delivered from the point of view of this one, because some message is used to generate this one, and that message did not be processed yet. Okay, so there's a causal dependency in there. Okay? mission 4241 or 3241 it's not processed yet, and this message depends on that one. Otherwise, the sequence number of this one cannot be found. Okay, so something is missing there. So again, you need to queue in the process D. Okay? That's the process, and then periodically, because whenever you receive message, you always update. Whenever you receive it, this corresponding vector element will always be updated by the new received message. Okay, so after some newly received message, this unsatisfied may become satisfied, or this unsatisfied may become satisfied, and then the message can be delivered. Okay, so that's basically this algorithm means. Okay, so this is cordial ordering broadcasting protocol. Okay, they use a vector to guarantee that this cordial order can be preserved. Okay, so we finish this message passing. Okay. We will stop here. Next week we will have a second midterm. Okay, and the scope is multi-processor systems, multi-computer systems, and distributed systems, and this message passing facilities. It's 4 lectures. Okay, and so you should start to prepare your exam. And if you have any good question and propose the answers in this scope, you are welcome to submit to send to me through my email address. Okay, do not use the E3. Just send through the email directly to me. Okay, that is enough. So please send it before the noon of the Saturday. Okay, okay, Saturday is good enough. Okay, then I have time to prepare. Okay, so we will stop here. Good luck for the second exam.
说
什么？
说的要请他们帮忙处理吗？
都可以说，每个人都。
不，意思说他
他们都有修过吗？
应该佳音的话我不知道，但是恒毅跟雨辰都有修过。
对，
那我到时候就请他们也协助帮忙出题。对，好。所以老师，我明天10点的时候到你的办公室嘛？对，然后。